Hi, so for today we are going to talk about logic circuits and switching theory, and we are going to talk about specifically logic gates. So last time we have discussed number systems and the introduction of logic circuits, and now we are going to logic gates. Okay, so what are gates? Basically, the gates in digital electronics are they perform specific functions, okay, between two or more inputs, specifically for AND gate, OR gate, XOR gate, XNOR gate, uh, and many more gates. But logic gates can also perform in just one input, just like the inverter, of which or what we call the NOT gate, wherein if we have a 1 as an input, the output will be always negated or inverted. So if we have an input of high, the output is low. And vice versa, if we have a low input, the output is high. So basically, these are gates that perform operations on the inputs. So let's get started. So the very first thing that we need to take note is the inverter or the NOT gate. So the inverter or NOT circuit, as they call it, performs the operation called inversion or complementation. So that is inversion or complementation. Okay. So in the Boolean algebra, we may see a bar or a prime. Okay, it means that if we have a value of 1 of a, then the a bar or the a complement will be 0. So it inverts whatever input. We know that we only have two inputs, 0 or 1. And logic 1 is considered as high, logic 0 is considered as low. So whatever is the input, the output will be the complement or the other digit. So the inverter changes one logic level to the opposite level. Okay? So in terms of bits, it changes a 1 input into a 0 output and a 0 input into a 1 output. So hence the word invert. Okay? So standard logic symbol for a NOT gate is given by this schematic symbol wherein we have a triangle here and a bubble here. So basically that's the inverter, or sometimes it's written as this, but most commonly this is written as the schematic symbol for the inverter is the first symbol. So the truth table for an inverter, okay, let's say we have A and as our input and our output is this. So the truth table, the truth table contains all the output and input in a given logic circuit. So if you have an input of 1, the output is 0. And if you have an input of 0, you have an output of 1. Likewise, if you have logic low as the input, the output will be high or logic high. Or if you have logic high as input, you have logic low as the output. And that is the inverter or the NOT gate. Okay? So when the input is low, the output is high. And when the input is high, the output is low, thereby producing an inverted output pulse. For example, if you have an input pulse such as this, which corresponds to logic high or logic 1, the output in terms of pulse will become like this. So you have a logic 0 for the output pulse. Hence, inverter. So the logic expression for an inverter, just like what I've said, in Boolean algebra, of which that will be our next topic, it uses variables and operators to describe a logic circuit. So if we have an input A, whatever that A may be, let's say in terms of logic circuits, it's only 1 and 0. Okay? So whatever the value of that A, we have an output that is an inverted output. So you have A bar or you have A complement. Okay? So whenever we say complement or not, okay, or inverted, okay, we know that uses an inverter because it inverts the input. Next in line, we have what we call the AND gate. Okay. The AND gate can have two or more inputs. Okay, and by the way, the inputs or the number of possible inputs is given by this equation. Okay, 2 raised to n, where n is the possible number of inputs, and the result would be n, of which that will be the number of combinations in terms of bits. Okay, number of combinations of bits. So an AND gate can have 2 or more inputs and perform what is known as logical multiplication. So whenever we think of AND gate, it's multiplication. Okay? In terms of its operation. The AND gate is composed of 2 or more inputs. Of course, when we use AND gate, we should have 2 or more inputs. Just like what I've said, the number of possible combination will be 2 raised to n. Okay? So basically, if you have one input, you only have 2 raised to 1. The number of possible combination will be only 2, which is 0 and 1. If you have 2 possible inputs, you have 2 raised to 2. You have 4 possible inputs, okay, or possible combination of inputs. If you have 3 inputs, you have 8 possible combinations, and so on and so forth. So for the AND gate, the minimal requirement is that you should have 2 inputs, and it produces a single output, as indicated by the standard logic symbol shown here below. So this is the standard logic symbol for the AND gate. What does an AND gate do is that it logically multiplies the inputs. So for example, if you have an input of 0 and another 0 here, 0 times 0 would be 0. So if you have a low input, okay, both low input, undoubtedly it will produce a low output, because 0 times 0 would be 0. And the same, what happens is if we have a logic 0 input and a logic 1 output input ANDed together, or AND together, since 1 times 0 and AND gate performs multiplication, so the output is still 0. The only time that the output of the AND gate will be high if both inputs are high. If there is one input, okay, if there is one input that is low input or logic 0, the output will always be 0. So for an AND gate, output X is high only when inputs A and B are high or 1. X is low when either A or B is low. So if there is a logic 0 among the inputs and you perform AND gate, okay, the result will always be a low input or low output when both A and B are low. So the truth table for this AND gate can be seen as this. So as you can see, we have 4 possible combinations. Okay, so we have 0, 0, 0, 1, 1, 0, and then 1, 1, because we have 2 inputs. So 2 raised to 2 would be 4. So that will be the 4 possible inputs. Okay, this is the truth table. So if you have A and B as 0, 0, the output will be 0, because 0 times 0 would be 0. And if you have 0 and 1 as the input, you still have 0, because one of your input is 0. And if you have 1 and 0, still your output is 0. And lastly, if you have both high, both logic 1, that is the only time that the output will be 1. Alright? So that is the AND gate. So if you're going to do the 3 inputs, A, B, C, let's say, you'll be having a truth table that is in 8 combinations of 0, 0, 0, 0, 0, 1, 0, 1, 0, okay, 1, 0, 0, 1, 0, 1. Now that will happen, okay, until you reach 1, 1, 1. So if the output of AND gate for a 3 input will only be 1 if all of the inputs are high or 1. That is the AND gate. Alright? And the number of inputs, just like what I've said, the total number of possible combinations of binary inputs to a gate is determined by the following formula, where n is the number of possible input combination equals 2 raised to the small n, of which n is the number of inputs, okay, or the input variables. So for two input variables, you have four possible combinations. We have seen it a while ago here. This is 1, 2, 3, 4. Okay, because we have two inputs. And for three possible combinations or input, you have 8 combinations. And for four input variables, you have 16 combinations. Okay? So, for example, develop a truth table for a 3-input AND gate. Okay? And determine the total number of possible combinations for a input AND gate. So, what are we going to do here first is to develop a 3-input AND gate. So, we have 3 inputs. So, the number of inputs is 3. Therefore, the number of total combination is 2 raised to n, which is 2 raised to 3, which is 8. Okay? So, I'll start with inputs A, B, and C. Now, using the binary, you have 1, 1, 1. This is 2 raised to 0, 2 raised to 1, 2 raised to 2. This is such a good guide, okay, for the possible combination of, unique combination of the inputs. So, I'm going to try first. So, let's start first with 0, okay? The decimal number 0. So, we have 8 inputs, okay, 0 to 7. So, you have 0, 0, 0. The next one is 0, 0, 1 because of we have 1 only here. And the second one is 0, 1, 0 for 2. Okay. How about for 3? We have 0, 1, 1. That is for the decimal number 3 converted into binary. And then for 4, we have 1, 0, 0. 2 raised to 2 is 4. And then for 5, we have 1, 0, 1. 2 raised to 2 plus 2 raised to 0. So 4, 5. And then you have, this is 5. And we have 6. Okay, we have 1, 1, 0. And then finally, okay, we have 7, which is all 1. Okay? 1. Oops. I only have 1, 1, 1. Okay? So, for the last input. So, the output, obviously, for an AND gate, we know that the output of the AND gate, if there is a logic low on the inputs, among the inputs, we know that that would be, the output would be low. Okay? So, we have 0 times 0 times 0 would be 0. So, you have 0 here, 0, 0, 1. Still 0, because 0, 0, 0 times 0 is 0 times 1 is still 0. So, you have 0 here. You still have 0 here. 0 here because we have one input, that is 0. And here, 0, we have an input of 0. The only time that it will be high is if all of the inputs are high. So, this is now the truth table for 3-input AND gate. Okay, so that is our answer. For number 2, determine the total number of possible combinations for a 4-input AND gate. So, 4 input, we have 4 input. The total number of possible combinations is n raised to equals 2 raised to n, which is 2 raised to 4, of which that would be 16 combinations. So, the total combinations, possible combinations for a 4-input AND gate would be 16 combinations. Okay? So, AND gate operations with waveform inputs. This is an example of an AND gate operation with a timing diagram showing an input and output relationship, wherein we have inputs A and inputs B. Okay? So that we have inputs A and inputs B. So, by the timing diagram, we can determine the output by the timing diagram or by the pulse width. T sub 1, T sub 2, T sub 3, T sub 4, T sub 5. In T sub 1, we have both of the inputs A and B, which are logic 1. So, therefore, we are expecting an output of 1 also. But in the case of the second T sub 2 of input A, it becomes 0. And still, the input B is still 1. So, what do we expect? The output will be 0 because we have an input that is 0. And on the T sub 3 of input A, we have 1, both 1. So obviously, both high. So we have another input or output of 1. And for T sub 4, the input A is still high, but the output B is low. So 1 times 0. So we expect that the output here in T sub 4 would be 0. And lastly, A input would be 0 or low, and the B input is 0. So technically, still, in T sub 5, the output would be 0. Okay, so that is the AND gate operations with waveform inputs. And so we have a simple seatbelt alarm for the AND gate applications. Okay, so we have two inputs here. For example, you have the ignition switch, you have the seatbelt. Okay, so for the ignition switch, it will be high if that is on. So in other words, if the ignition switch or if you start the car, it will be a logic 1. Okay, so the application is that the alarm will alarm when you open the car and then you have an unbuckled seatbelt, of course. Okay, so the logic 1 high will be the unbuckled seatbelt. Okay, and if you are buckled, then it's logic 0. Okay, so if you don't switch on the car, then that is still for the input A is low. So for the seatbelt to alarm, both should be the ignition switch is okay or open, and at the same time you are driving unbuckled. So it will alarm because it will perform what? The AND gate. Okay? So basically, if you have 1 and 1 here, and then you have an AND gate here, and you have a timer here that ignition on high for 30 seconds. For example, you just open it for 30 seconds, and then your seatbelt is unbuckled. The timer diagram will always be high for 30 seconds. And inputting all the A, B, and C here will produce an output that is high for an AND gate. So if one of the input is low, for example, the seatbelt is buckled. Okay? So if the seatbelt is buckled, okay, then there will be no alarm. Okay? If the ignition switch is off, then there will be no alarm. Okay? So, yeah, we can use AND gate for this simple seatbelt alarm. Next gate, we have the OR gate. For an input, 2-input OR gate. Okay, the OR gate, in contrast with the AND gate, what it does as operation is addition, binary addition. Okay, so for a 2-input OR gate, output X is high when either input A or input B is high. So in other words, if one of the input is high, definitely your output will be high. The only time that the output for an OR gate will be low is that if you have both low inputs. Otherwise, it's high. Okay? So let's take a look at the truth table, and of course the symbol of the OR gate is this. It differs from the AND gate, of which this is the AND gate, and the OR gate has something twist like that. Okay, just like this. Okay, so as you can observe, for a 2-input OR gate, which has 4 possible combinations, when we have an input of high, it will always produce high or 1. Okay, so yeah, the only time that the output will be low is if both A and B are low. Okay, so that is the OR gate. Okay, so it basically performs addition or plus in the OR gate or in the Boolean algebra. So the OR gate operations with the waveform. So what if we have two waveforms, A and B, separated by or inputted into an OR gate? So what happens here is that both, okay, in T sub 1, both of the inputs are high, so definitely the output is high. In T sub 2, one of the input is low, A is low, but still the B is high. So if we have either of the input that is high, the result will still be high, or the output. Okay? In the T sub 3, both of the inputs now become 0. So the output of X would become 0, or the OR gate. And lastly, for the T sub 4, we have another high for logic, or for the input A, and another low for input B. So what happens? Still, this will be high. Okay? Because as long as there is one input that is high, the output for OR gate will be always high. So if the two input waveforms A and B in the figure below are applied to an OR gate, what is the resulting output waveform? Okay? So of course, there's no question with that. So if you have 1, you have 0 here, 0, 0, 1, you have 0, 0 here. Okay, and then you have 0, 0, 1, 0, 0, 0, 1, 0 here. Okay? So 1 plus 0, as long as one of the inputs is high, then definitely we can have it as high. Okay? And then this would be 0, this would be 1, this would be 0. Of course, this would be 1, this would be 0, and this would be 1. Okay? Of course, we have 0, 0 here, so we have 0 here. So that will be the output, okay, waveform for an OR gate. Alright, so that's the result, okay, of the waveform. OR gate application. For example, you are setting up a security system in your house. And of course, you have sensors for different windows. Let's say you have 3 windows. Okay, of course, if one of the windows, if the thief tries to break through one of the windows, the alarm should be activated, of course. Okay? We don't want to wait at least two windows, or all of the 3 windows should be opened, okay, before the circuit alarms. No. Only one, if only one of the windows, okay, becomes open, okay, definitely we have a thief coming into our house. Okay? So that if we have 3 windows as our inputs A and B and C, and the logic high is that the windows are open, and the logic low is the windows are closed. If one of them begins to high, let's say 1, 0, 0, in your window A, someone barged in, definitely if these inputs are connected into an OR gate, okay, if we have an input of 1, 0, 0, then definitely the input is 1. If this goes high, there will be an alarm circuit. Okay? So that is one of the applications of the OR gate. But definitely, so that's ideal, that's logical, that if one of the windows open, it should alarm. So we also have what we call the NAND gate. Okay? The NAND gate is simply not AND. Okay? We just simply invert what is the output of the AND. So that if we have 1 times 0, okay, we have 0 for an AND, but in a NAND gate, it will be reverted. So if we have 1 and 0 as input, and then we AND it, that the output is 0, and we NAND it, then definitely the output will be 1. So the only time that the NAND gate will get 0 is that if both inputs are high. Okay? So the NAND gate has this schematic symbol wherein we have an AND gate and we have a bubble just right beside the AND gate. And that includes, and that indicates that that is a NAND gate, not AND gate. So if you're going to look at the truth table of this NAND gate, so you can see that if both A and B are high, Because if you AND it, if you perform AND, 1 and 1, that would be 1. But if you perform NAND, it simply gets the complement of 1, which is 0. Okay? So the only time that the NAND gate will be both, okay, will be 0 is that if both of the inputs are high. And the negative OR, okay, is the equivalent of NAND. Okay? So these two gates are equivalent, the NAND gate and the negative OR. So what the negative OR does is that if we have a NAND gate of 0 and 0, okay, if we perform AND, we know that the output will be 0. But still, since this is NAND, the very output will be 1. So let us try also if we input 0, 0 here. Okay? Since negative OR is equivalent to NAND. So if I input 0, 0 here, we have an inverter here, so it becomes 1 and 1 here. If we OR, what? If we try to OR 1 and 1, the result will be, okay, 1. So they have the same output. Okay? So if you try through all of the combinations of bits, you will find out that they have the same output. So the negative OR equivalent is equivalent or equal to the NAND gate. So for example, for the 4-input NAND gate operating as negative OR gate, determine the output with respect to the input. So as you can see here, NAND gate is equivalent to the negative OR. Okay? So negative OR. So for the negative OR, if one input is high, of course, what will happen? Okay, we know that the result will be low. So let us try. So we have for letter A, timing diagram, you have 0, you have 1 here, you have 1 and 1. So if you're going to look at it, you have 0, 1, 1, 1. This becomes 1, 0, 0, 0. And if you OR that, the result would be 1. Okay? Okay, because this is OR already. Okay? We have inverted the inputs such that it becomes 1, 0, 0, 0, 0. And then we have ORed it, we have 1 as an output. For the second one, we have 1, 1, 1, 1. All of the inputs are 1. So if you negate it here, before it enters the OR gate, that would be 0, 0, 0, 0. So that if you OR all of this, the answer would be 0 here. Okay? So the next one, we have 1, 0. We have 1 here and 1. So 1, 0, 1, 1. So 1, 0, 1, 1 becomes 0, 1, 0, 0. At least one of the input is high. If you ORed it, it will still be 1. And so on and so forth, so that the negative AND gate is equivalent still to the negative OR gate, or NAND gate equals NOR, or negative OR equivalent. Okay? So these two are basic. Okay, basically equal. So the logical expressions for NAND gate are given as follows. So the Boolean expressions for a 2-input NAND gate is this, wherein the output X equals AB complement. Okay? So meaning, you have AB complement. You're going to multiply A and B, then you're going to get the complement. Let's say, if you have A equals 1 and B equals 1, so you have 1 times 1 complement. 1 times 1 would be 1, and the complement of 1 would be 0. So that's why here, 1 times 1, we have 1 times 1 complement. Okay, 1 times 1 is 1. Complement will be having 0. So if you have 0 times 0, okay, you have 0 times 0 would be 0. Complement of 0 would be 1. You have 0 times 1. 0 times 1 is 0. Complement of 0 would be 1. And 1 times 0 would be 1 times 0. 0 complement will be 1. That is the logic expression for NAND gate or negative OR. Okay? Negative OR equivalent. So we also have the NOR gate. Okay? So last time we have NAND, negative AND. Now we have negative OR. So for a 2-input NOR gate, output X is low when either A or input B is high, or when A and B are high. X is high only when both A and B are low. So for a NOR gate, it's just simply operation of OR or plus, and then after OR, after you have ORed the two inputs, you're going to get the complement. Let's say we have, okay, for A and for B, so you have 0, 0, 0, 1, 1, 0, 1, 1. Okay? So, if you are going to have a NOR gate here, output, so you're going to OR first. 0 plus 0 is 0. And then get the negative, since it's a negative OR, so it becomes 1. So, 0 plus 1 is 1. And then get the negative of 1, which is 0. So, you have 1 plus 0 is 1. Get the negative of 1 would be 0. And 1 plus 1 is still 1. Get the negative of it, it will be 0. So, the only time that it will be high, only when the inputs A and B are low. That is the NOR gate. Okay, the NOR gate is represented by the schematic symbol of OR with a bubble after its OR symbol. So here is the NOR gate truth table, just like what I did a while ago. Okay, the output will only be high if both of the inputs are low. Okay, so NOR gate with input waveforms. If two waveforms shown in the figure are applied to NOR gate, what is the resulting waveform? So again, we know that the NOR gate will only produce high, okay, if both A and B are low. So, of course, the output X will be high because 0 plus 0 would be 0, and then you negate it, that will be 1. So, unless otherwise, okay, it would be 0. So, if you have 1 and 0 here, okay, the OR gate, the NOR result or the NOR gate result will be 0. So, you have 0 and 0 here, of course, that is 1. You have 0 and 1 here, of course, that is 0. You have 0 and 0 here, of course, that is 1. You have 1 and 0 here, of course, that is 0. And you have 0 and 0 here, of course, that is 1. So that will be the result of the NOR gate. Okay? Or, in other words, if you're just being confused, perform first the OR, and then negate or get the complement of each of the result. That will be your NOR result. Okay? NOR gate result. And the NOR gate has an equivalent of negative AND. If a while ago we have NAND equivalent to negative or negative OR, now we have a negative or NOR gate, not OR, okay, equivalent to the negative AND. So let me show you by having a simple output of, let's say, you have A and B, and again you have an input or output of X, okay? So if you have 0, 0, 0, 1, 1, 0, and then 1, 1, okay, what will be the output? X. So of course, we already know that if we do that for a NOR gate, the output will only be high if both inputs are low. So in this case, that would be 1, 0, 0, 0. Okay? So for negative AND, let's try to have a truth table just for us to show for the negative AND. So the negative AND performs what? Negative first, and then you AND. Okay? You AND gate it. So we have 0, 0, 0, 1, 1, 0, 1, 1. So if you input 0, 0 here, okay, before it reaches the AND gate, it becomes 1 and 1. And the 1 and 1 will be ANDed or will be multiplied. So the output result would be 1. So this is for negative AND. We are proving that the negative AND is equal to the NOR. So how about if you have 0 and 1 here? Okay, if you have 0 and 1 here, of course, the result still will be 1 here. And the 1 input here would be now 0 here. So 1 times 0 would be 0. Same result if you have 1 and 0 here. Okay, what will happen? This would be 0. and this would be 1. So 1 times 0 would be 0. And lastly, if you have 1 as inputs, okay, so you'll be having 0 and 0 both here. And you add zeros in 0, that would be 0. So as you can see, the output is still the same for NOR gate and the negative AND gate. Okay, so that we conclude that these two, NOR gate and the negative AND, are simply equivalent. So the logic expressions for a NOR gate is given as follows, so that we can see the Boolean expression for the output X will be equal to A plus B complement. So if for NAND gate, we have seen it that X will be A, B complement. For a NOR gate, it will be A plus B complement. So that if you analyze 0 plus 0, okay, 0 plus 0 is 0, complement, that would be 1. And you have 0 plus 1 would be 1, complement of 1 would be 0. 1 plus 0 is 1, and the complement of 1 is 0. And 1 plus 1 is still 1, the complement of 1 is 0. So that you have an output of 1, 0, 0, 0. Okay? For at least 2 input given expression. Okay? So I hope you are learning something for the logic expressions. And we have also XNOR, or the exclusive NOR gate. Okay? So for the exclusive NOR gate, okay, we will only have a high output. Okay? For the exclusive NOR. This is different from NOR. This is also different from NAND. Okay? Or. We have an exclusive NOR gate. For exclusive NOR, okay, this is also different from XOR. This is exclusive NOR. For exclusive NOR, we only have a high output if the inputs are the same. Okay? So if the inputs are the same, we have high output. That's XNOR. So we have for 0 and 0, we have high output. With 1 and 1, we have high output. The rest, if they don't have the same input, okay, that is 0. What if we have another input, C? So let's say A, B, and C. If you have 0, 0, 0, okay, it's still 1 because all of the inputs are the same. And if you have 1, 1, 1, all of the inputs are still the same, then definitely we still have 1. But if we have 0, 1, 0 and 1, 1, 0, the case is the output will always be 0. So for an XNOR gate, the output will only be 1 or high if all of the inputs are the same. Okay? So, it's basically an exclusive OR, okay? Okay, how about for XOR? Okay? So, disregard these inputs and outputs. So, basically, I'm going to, or the output only, okay? I'm going to have a truth table, okay, corrected in this slide. For the XOR, okay, it's kind of different or just the negation of the XNOR. So, if the two inputs are the same, we have 0. And if they are different, we have 1. 1 and 0. So that's just simply it is. Okay? So for an XOR, the output will be high if the inputs are different. Okay? So if they are different. And the output will only be low if the inputs are the same. So that is for an XOR. Okay? So let's try to determine the XOR, exclusive OR. And at the same time, we graph also the XNOR, which is simply the negation of what is the XOR. So we say, for an XOR, okay, we will produce, okay, high input or high output if the inputs are not the same. Okay? So you have 1s and 0 here. The inputs are not the same. Then definitely we have a high XOR for the output of XOR. But for if we negate that to get the XNOR, that would be 0. for the XNOR. All right? So, because for the XNOR, if the inputs are the same, that will be the time that they will be 1. Okay? So, we have 1 and 1 here. For XNOR, it is 1. Of course, they are the same. For XOR, it will be 0. For this, we have 0 and 1. So, this will be for the XOR different will be 1, and get the complement, that will be 0. So, you can, in order for you not to be confused, you can just get an idea of XOR. And then, whatever the result of XOR, that you negate it, that will be the XNOR. Okay? So, you have 0 and 0 here. Definitely, this will be 0 because they have the same input. Okay? So, for the XNOR, it will be negated. It will be 1. So, we have, again, 1 and 0 here. So, they have difference. So, this will be XOR for 1. For the XNOR, it will be 0. So, you have 0 and 1 here. So, you have also XOR for 1 again. They are not the same. So, the output is high. So, if you XNOR, that would be 0. So, that is just simply the relationship between the XOR and the XNOR. And again, for XOR, if the inputs are not the same, okay, then the output will be high. And the negation of that will be the XNOR. Okay, and that is all. I hope you learned something from this video. Thank you so much for listening. Again, this is Engineer Abat. See you again on the next video. Bye.